Welcome to the second calculus video on differential equations, which is about slope fields. The graph in front of you is an actual slope field. On the x-axis we label x, and on the y-axis we label dy dx, or y prime. And usually slope fields we have two different types. One of them we have the actual connected curve, and so you see actually multiple connected curves here. Or in a moment, I'm going to show you a disconnected curve which has just multiple linearizations that we ultimately connect to create the solutions to the differential equation. But what's a little bit hard to wrap our brains around is the fact that what's in front of you is the actual solution to some differential equation. And by constructing a slope field, you actually help to find out the actual solution. But more specifically, or directly, a slope field is a graphical way to find out the solution to a differential equation. So let me show you a little bit how and why. So on this graph, if I just delete or just erase a bunch of this slope field here, we'll end up seeing just little linearizations. It's hard to say, little linearizations. And I think you already know the actual curve that you see here is the cosine curve. And I'll just erase that whole thing there. It's disappearing before your very eyes. And the tick marks that I have on the graph are every pi over 2. So if we were to actually start with an equation here and sketch the solution or sketch the differential equation, we would get a bunch of these little linearizations. Now we may only do like 2 or 3 vertically and 2 or 3 horizontally, but you get the idea. The more you do, the better you can see the curve. So then I could connect them together and just kind of follow the slope field or the linearizations to get the cosine curve that you might have seen a moment ago. Since there are an infinite amount of general solutions to a differential equation, that's why we see multiple solutions on this graph, which happen to be cosine x, the regular cosine x curve, which is actually right there, or cosine x plus maybe 3, cosine x plus 6, and cosine x minus 3 right there. As far as we're concerned, though, we're mostly going to be doing two things. One is constructing a slope field for a specific differential equation, or matching a slope field with an equation and some sort of description of that slope field. The slope field, differential equation, something about the graph, and so on. So what I'd like to do now is just teach you how to construct a slope field from this equation. And the way that we're going to do it is really similar to sketching just a regular function and creating a table of values. So if we're to construct a slope field for dy dx equals whatever, cosine x for example, then we're just going to do that. We're going to set up that table x, y, and then in the third column or third row, depending on how you set it up, we're going to leave an option for dy dx. Now for you, if you're taking notes specifically on this video in a booklet, then you may want to create your table going sideways, meaning x, y, dy dx going down, and then you'd have this table going horizontally. So the first thing I want to point out about this particular equation is that the differential equation is based on x. It has absolutely no difference what y value we plug in here on the curve that we sketch. So that's why I only have one column for y. If it's based on x and y, you might have a whole bunch of different columns and rows to fill in. So let's go ahead and just consider 0, pi over 2, all the way up to 2 pi, and we're going to try to sketch this kind of in this right area here. So if we were to just plug in 0 into cosine, we get 1. And if we're going to plug pi over 2 into cosine, well, cosine pi over 2 is 0. Cosine pi, it's reached its minimum. Cosine 3 pi over 2 is also a 0. And cosine 2 pi is 1. Oh my goodness, I put those in the y column, sorry about that. So what I meant to write for the y is anything, any value. So when we sketch this slope field, it's going to be 0, 1, 0, 2, 0, 3. It's all going to have the same slope at those points. So notice on the right side, this third column, we have dy dx. So we're going to plot 0, 1, pi over 2, 0, and so x, dy dx. So the next thing we'll do, we'll just sketch a coordinate plane here so that we can plot some linearizations. Okay, here we go, 0, 1. So at 0 we have a slope of 1. So we'll sketch a little linearization that has a slope of 1, as if we're sketching y equals x. And we're going to do that at each of the y values. So at positive 2, 1, 0, and negative 2, and negative 1 all have a slope of 1. Kind of tricky, 1 and 2 don't really look too much different on a slope field, but 1 and 8 should look quite different, or 1 and 50, who knows what it would be. So pi over 2, 0, we're just going to do a little linearization that's flat, a horizontal. And on many slope fields, in black and white paper, you can't actually see a horizontal linearization. Alright, so then at pi, notice at pi it's going to be negative 1, so I'm going to go the other direction, so tilting down. So just a little mini line. And at 3 pi over 2 we have 0 again. We're not really thinking about what this is too much, although you might have an idea. We're just sketching the values. And then 2 pi, 1. So there you have it. You have a slope field based on the differential equation cosine x. Now, like what I said a moment ago, is if you start at one point, I'm going to go up here and start at 1. I'm going to start at this point. I'm just going to follow the slope, so it's forcing me to kind of go towards the next one. And once I get to the next one, I'm going to just be horizontal for a moment. And then it's like the tide is moving. It's forcing me to go the other way. And it's bringing me back down. And I keep going until I sense the next slope, which is 0. And I'm 0 for a while. And I'm sensing the next slope, which is 1. And so what you see in front of you that's a sine curve. So that means sine is a solution to cosine x, because when we sketched the slope field for cosine x, it gave us the sine x curve. Let me say that again. I sketched the slope field for cosine x, and when I connected the linearizations, it gave me a solution curve, which is sine x. So if sine x plus 1 is the one that I actually sketched there. So that's how to sketch or construct a slope field by hand. Now many times we're just trying to match them up or fill in a graph based on that. Alright, what I like to do is just end with a few tips for working with slope fields. The first one is that when you're matching slope fields to the actual equations, when you're trying to do that, which is kind of one of the main things we want to do, when matching, you just want to try points in each quadrant. So you're just going to pick a point in a quadrant and plug that point into the actual differential equation and find out if it matches up with the information. In other words, so you take 1, 2 and you plug it in to the actual equation and then see if it gives you the slope that is sketched on the graph. Alright, plug that in for each quadrant. 2 more here. Look for asymptotes. Look for asymptotes on the graph. So sometimes you'll see a bunch of the slopes, the linearizations are flat, so that means there's an asymptote over there. I'm telling you, it must be hard to talk and speak. And the last one is kind of like what I mentioned before. Horizontal linearizations can't be seen on a graph. Specifically the x-axis on a graph. So it may be difficult to see maybe a vertical linearization on the y-axis as well. Alright, so those are just a few tips. We're also looking out for common shapes that we're familiar with, like parabolas and circles and hyperbolas and things like that. So there were some tips, and that is all I wanted to share with you about slope fields. Thank you for learning with me.